Okay, so the next chapter we're doing is thermoelectric effect. And from now on, the thing that used to be here is also not there, so it's good. There's a better view in the video. So let's start. The thermoelectric effect is the shortest chapter in grade 12 physics, so it won't take long, and I will do both theory derivations and numerical short questions in the same video. So let's start off with the primary definition of thermoelectric effect or Seebeck effect. It is also called Seebeck effect. Thermoelectric or Seebeck effect. It is the phenomena of production of electric current in a thermocouple when two junctions are kept at different temperatures. Imagine a thermocouple just like this, and these are the two junctions with these are wires of different materials, and there is a galvanometer in the middle to detect the current flow or not. And one junction is at cold temperature and other is at hot temperature. So it can be defined as it is the phenomenon of production of electric current in a thermocouple. When its two junctions are kept at different temperatures. This is the definition of thermoelectric effect, and what we don't know is a thermocouple. So we can define thermocouple as well. Thermocouple is formed. It is like a device. It is formed when two wires of different materials are joined at their ends. Yeah, that is a thermocouple. And now we can simply go to the this is the center. Okay, and now we can go to the origin and cause. Cause of Seebeck or thermoelectric effect. And by the way, the current produced is called thermoelectric current, and the induced in EMF produced is called thermo EMF. That's what you all need to know. So now we are going to the next portion, and that is origin and cause. So the cause is basically the related to the electron diffusion. So let me read it out for you all. Different metals have different number density of free electrons. When two wires of different metals are joined, the electron will diffuse from higher density to lower density through the junction, so that the potential is established at the junction, called contact potential. When two junctions are kept at same temperature, the contact potential at the junctions will be same, as being the rate of diffusion same, so that the potential difference will be zero. Hence, no current flows to the thermocouple. However, when two junctions are kept at different temperatures, the rate of diffusion of electrons through the junction as well as the contact potential will be different. The difference in contact potential of two different junctions appears as a thermo EMF, and hence current will flow through the thermocouple. So to summarize, you can write that different metals have different number density of free electrons. So the electrons, so when two different wires of different metals are joined together, when they are joined together, the electrons will flow from higher density lower. When the temperature is lower and a potential is established. When the temperature is same at both junctions, the contact potential will be same. That means the potential of contact of electrons will be same, ensuring or which leads to being same and diffusion rate of electrons. So no PD is developed. However, when a temperature difference is introduced, what actually happens is the rate of diffusion as well as contact potential of electrons change, that develops a potential difference and the current So you basically summarize everything this much and write this for 2 marks questions. Yeah, you may read it and summarize it yourself. Now let's go to the variation of thermo EMF with temperature. Thermo EMF varies with temperature on the there are two factors that depend upon that change the variation. That is, let's consider of iron copper thermocouple, one junction of the thermocouple. Let's consider a iron copper thermocouple. One junction is placed at 0 degree and the other one is at theta degree. This is ice, melting ice, and this is the temperature of hot oil. So what happens here is, in this case, if the temperature of hot junction is gradually increased, this one is 0 but this one is gradually increased, what happens is the thermo EMF induced here, the thermo EMF, the galvanometer shows the reading. The galvanometer is like this, and here is a needle. So when the temperature is gradually increased, the needle goes on increasing. That means it indicates that there is a higher potential difference and the current flowing is higher and stronger. So it increases while increasing the temperature. That means temperature difference increases the current flow. And when the temperature of hot junction at which thermo EMF becomes maximum, at which there is a certain temperature where the the thermo EMF becomes maximum, that is called neutral temperature and denoted by theta n. And when the temperature of hot junction is further increased, when it is increased above the neutral temperature, the value starts to decrease. So and gradually then becomes 0. So if the temperature of hot junction is again increased, thermo EMF reverses direction. That means what happens is when you increase the temperature from smaller temperature to the highest temperature, that is theta n, where the value of current is maximum, and if you keep on increasing, it decreases. The I decreases when theta n is too high, and after a certain point the temperature starts to inverse. That means the direction of current starts to inverse. That means like on very high temperatures, the theta n increases. On increasing theta, it becomes theta n. First of all, it becomes theta n, and if it is even increased after theta n, then it becomes theta I, called temperature of inversion, where the direction of current starts to inverse in the opposite direction. The temperature of hot junction at which thermo EMF becomes 0 and reverses its direction beyond it is called temperature of inversion. The temperature of inversion depends upon nature of metals forming thermocouple and temperature of cold junction. This is the most important part of this question. Temperature of inversion. The temperature of hot junction in which thermo EMF becomes 0 and starts to reverse its direction beyond it is called temperature of inversion. The temperature of inversion, it depends upon two factors. Theta I depends upon two factors: nature of metals and temperature of cold junction. Now similarly, we can define the other terms, such as this one is very important. The other terms such as neutral temperature. Neutral temperature is the temperature of hot junction at which produced is maximum. So that's it, and it depends upon only one factor: nature of metals. It does not depend upon the temperature of cold junction. It is independent to that. So now we need to go to the relation between, we are now going to the relation between theta I, theta n, and the theta c, the temperature of cold junction, inversion temperature, and the neutral temperature. The relation is simply, you don't need to derive this or anything, you just need to remember this, that is theta n will be equal to theta c plus theta I by 2. This is, how can we remember this, is there is a thing called NIC Asia. You can see NIC, right? So N will be equal to IC, that is N will be equal to theta I plus theta C by 2 theta N. That's a cool mnemonic, isn't it? So yeah, just remember this bank. Now we are going to, yeah, you might, this is the easy formula, but you might confuse the position of these, and if you mess up the position of neutral temperature with either of these, you will make a mistake. So you can just use that mnemonic for your better marks. Now we have another thing called thermoelectric series, and after that the chapter ends. So we'll do some numericals and that's it. Alright then. Thermoelectric series. Thermoelectric series is the series of the elements or metals that give least, that is the series which can be used to determine the magnitude and direction of the thermoelectric current so produced. So it is defined as the, in order to determine the magnitude, direction, and thermoelectric current of the EMF, metals are arranged in a systematic or called the systematic arrangement of metals for the determination of the magnitude and direction of the thermoelectric current produced is called thermoelectric series. That being said, now we can basically write the series. This is antimony, iron, and in the middle comes lead, and then comes copper, cobalt, nickel, bismuth. You need to just remember these two are the extremes. So the thermocouple that is made by using antimony and bismuth will be the best type of thermocouple. This is antimony and this is bismuth. Remember these two names might be asked in the MCQ. So that much is what you need to know. Okay, yeah, and the direction will be given by, from the metal that comes earlier to the metal that comes later. Magnitude, greater the gap, greater the magnitude. So the current that if there is two thermocouple like this, there is thermocouple, then the current flows from the metal that comes first in this series to the metal that comes after in the series, and the magnitude of the current is more is proportional to the gap between them. So the maximum current can be generated from the thermocouple made by SB, antimony bismuth. But these are not so common elements. So iron and copper. Iron copper thermocouple is the most used thermocouple today. So after that we have Peltier's effect, and after that we have okay. Peltier's effect. Peltier's effect is the phenomena. It is basically a phenomena of turning of, what is the word used? It is the phenomena of evolution. Yeah, evolution of heat and absorption of heat. In either of the two junctions, thermocouple, when a current is passed through it. When a current is passed, it is just the reverse of the Seebeck effect, so I don't think I have to tell anything else. And the cause is basically when the cause is also opposite. Cause, the current flows from higher potential to lower. So lower in one junction, look at this might have a higher electron density and this might have lower. So, and in this also the same thing happens. So in one junction the electrons go from this to this, and in the other electrons come from this to this. So since the current is passed, the electrons will move from this direction to the like this to this direction. So while they are moving, imagine here is higher electron density, and imagine this upper lower. So it is traveling from higher electron density to lower electron density in one junction, and from lower electron density to higher electron density in other direction in one junction, and vice versa in the other direction, other junction, my bad. So due to that, so in the junction, where it flows from higher potential to lower, energy is released and absorbed on flowing from lower to higher. So where the energy is absorbed, meaning cold temperature, and energy is released, meaning hot temperature. So that said, we are now moving on to the next thing, that is thermopile. Thermopile, you just need a thermopile. What is a thermopile? So thermopile is basically a device used to detect heat radiation. it works on the principle of thermoelectric effect. And how is it what is the principle of it is thermopile is a heat radiation detecting device, or what is device, yeah, heat radiation detector, DTECTOR, detector. It works on the principle of thermoelectric effect. How does it work? So when heat radiation is incident on one side of the thermopile, it thermopile, the current will flow. The thermoelectric current will flow through the thermopile. The thermoelectric current will flow through the galvanometer and flow through the galvanometer and deflects it. So since it is deflected, the heat radiation, if the galvanometer is deflected, the heat radiation is present, otherwise not. So if the galvanometer is deflected, the heat radiation is present, otherwise not. Applications. What are the applications of a thermopile? So it is used in thermoelectric generator, and it is also used in electrical appliances, to prevent overheating. Now we move on to the numericals, and there is only one type of numerical for this, so I will just do one numerical and that will cover everything. So yeah, so I'm going to do question number 1, which already covers everything. Let me write down the question real quick and I will solve it, and the video is over. That's it, this chapter is over. The temperature of two junctions of a thermocouple are, the temperature of two junctions of a thermocouple are maintained at 0 degrees Celsius and theta degree Celsius respectively. Just like that. Then the thermo EMF generated is given by the relation E is equal to 10 to the power minus 5 theta minus 0.01 into 10 to the power minus 5 theta squared. Okay, find the neutral temperature, temperature of inversion and maximum value of thermo EMF. Find the neutral temperature temperature of inversion and the maximum value of thermo EMF. So in this type of question, you don't see the question, you don't read the question, you just take this thing. You just take this relation given in the question and just write it. E is equal to 10 to the power minus 5 theta minus 0.01 into 10 to the power minus 5 theta square. And you write here one thing. For neutral temperature, the derivative of this with respect to theta will be equal to 0, or this will be the 10 to the power minus 5 theta minus 0.01 and 10 to the power minus 5 theta squared by d theta will be equal to 0. Or if you differentiate it, what will happen is, what is the differentiation of 2x? That is 2. So you just write 10 to the power minus 5 minus, you just write what is the differentiation of 2x squared? That is 4x, right? So 2 into 0.01 into 10 to the power minus 5, we write theta n here equal to 0. So what will happen here is the value of theta n will be equal to 10 to the power minus 5 by 2 into 0.2 into 0.01 into 10 to the power minus 5. This will come somewhere around 50 degrees Celsius, exactly 50 degrees Celsius. So that now we have theta n equal to 50 degrees Celsius, and we know that the relation is theta I plus theta c, NIC by 2. NIC is here, right? Theta n is 50 and theta I we need to find out, and theta c is 0 degrees given by the equation. So theta c is 0, so theta I by 2. So theta I is equal to 100 degrees Celsius. This is another answer. Now we need to find the maximum value of thermo EMF. We just put the value of theta n in this equation. If we put that, then what will happen is E will be equal to 10 to the power minus 5 into 50 minus 0.01 into 10 to the power minus 5 into 50 squared. This will come around 2.5 into 10 to the power 4 minus 4 volt. And this is the answer. That is it for this chapter. There is nothing else, and this is the shortest chapter of grade 12. We completed everything including numericals in like 33 minutes. So yeah, thank you for watching, bro.